Good morning, teachers and friends. We are RE Group 116 and we will be presenting our research project on the effectiveness of canards compared to strakes in this video. This is the content we will be going through. Justin will explain the reason for our choice of project.
High angle of attack aerodynamics is an exciting area to research. According to our literature, high AOA aerodynamics are a current trend in civilian and military aircraft design. Not only is it a recent field of study, but it also is highly significant in the practical realm. Put simply, high AOA aerodynamics refers to aerodynamic situations where the wing chord is at a great angle to the relative airflow. Good exploitation of the phenomenon can increase lift generation beyond what is possible in ordinary cases. What are the benefits of greater lift? It improves civilian aircraft safety by reducing unintentional loss of lift in low-speed flight and allows slower landings, while improving military aircraft performance with reduced stall and greater acceleration for turning, allowing aircraft to turn faster and tighter. High AOA aerodynamics can be exploited either with wings of sharp leading edges or high lift devices. However, sharp leading edges have poor aspect ratio, resulting in poor lift drag ratio. High lift devices, however, are much more effective, causing them to be the focus of our research.
To meaningfully contribute to the field, we first need to understand how canards and strakes work. According to our literature, both canards and strakes strengthen vortex separated from the main wing, delaying flow separation. It is interesting that even for wings with no significant leading edge vortex generation, downwash is also found to increase lift coefficient. We then encountered a gap in current research. While current literature generally claims strake wing configuration as more effective, there is indeed research claiming that canard wing configuration produces stronger lift. Such a contradiction was exacerbated by lack of literature on the comparative effectiveness of canards and strakes. Furthermore, there are gaps in past research. First, there was a lack of scope for luckering. Only high canards were tested against strakes, raising the possibility for others to outperform. Secondly, the lack of control variables was demonstrated by Brennan, Stroh, and Hummel, who gathered little information about experimental conditions. Song similarly showed lack of information in the exact dimensions and shape of the models. This may lead to hidden variables that may affect results drastically. Next, we will discuss our methodology. We used a wind tunnel to generate data on effectiveness of canards versus strakes. Wind tunnel testing would obtain quantitative data without much theoretical knowledge, so this appeared to be the best choice. As you can see, it is made up of the setting chamber, which laminarizes turbulent flow from the fan, the contractor, which speeds up the air, and the testing chamber, where experiments take place. Two additional components are the retort stand holding the high lift device in place and the weighing balance measuring the downward force experienced by the main wing. The goal of experiments is to investigate the impact of high lift devices on the lift generated by the main wing under varying conditions. The 3D models of main wing, canards, and strakes are shown. They are 3D printed out to improve experimental accuracy. To date, two tests have been completed. The first test investigated the effect of relative AOA with the independent, dependent, and controlled variables shown in this slide. The second test was a comparison between various high lift devices at AOA 60 with variables shown.
Attached is the following data we obtained for experiment 1. Surprisingly, with presence of canards and strakes at all AOA, the main wing obtained less lift. Compared to our literature and the real-world application of high-lift devices, this is certainly unexpected. This slide further explains the findings in experiment 1. At 0 degrees, we believe downwash produced a net detrimental effect on the lift generation of the main wing, while the increase to 20 degrees marginally improved lift performance due to reduced flow separation. Drastic reduction of lift from 20 to 40 degrees was caused by downward momentum transfer, while flow separation only occurred at 60 degrees, with the canards generating sufficient vortices to overcome momentum transfer, while for strakes only sufficient to counteract its effects. A few concepts used in our explanation need further elaboration. Downwash refers to redirection of airflow in a downwards direction. Due to the artificial reduction in angle of attack, the lift of the main wing was reduced, resulting in less lift for canards and strakes at zero relative angle. Compared to a literature where flow separation effects are optimized at 30 to 40 degrees, our high-lift devices only showed effect at 60-degree relative angle, prompting us to formulate the theory of delayed flow separation. This theory is supported by the lift generation of our main wing, which continues to increase from 40 to 60 degrees, while the main wing will have started to stall in our literature with our high-lift devices. We believe that the low airspeed in our wind tunnel has caused flow separation to occur at much higher AOAs, explaining our anomalous results. Another theory was formulated to explain the drastic reduction of lift from 20 to 40 degrees relative angle. We believe that similar to downwash, downward redirection of airflow resulted in net negative force on the main wing. However, significant relative angle causes airflow to transfer downward momentum to the main wing instead of reducing the AOA, resulting in much more significant lift reduction. While lacking experimental support, this theory would hold true as long as there is significant airflow reduction by the high-lift devices. From our current analysis, we conclude that canards is a more effective high-lift device. However, due to limitations with experimental apparatus, high AOA was necessary to demonstrate this difference. However, our second experiment at 60 degrees AOA added new factors. Canards and strakes failed to show significant differences in lift performance, instead showing net negative high lift capabilities. The first observation seemingly contradicts with our results in the first experiment, while the second observation undermines our theories of momentum transfer and delayed flow separation. Since with no relative angle, the vortices occurring at 60 degrees AOA should be able to overcome downwash quite easily and produce positive lift. However, this contradiction was resolved after further analysis. As seen from the image, vortices generated by high-lift devices break down after a certain distance, causing its effect to be lost. Due to the slow speed of our wind tunnel, vortices from high-lift devices break down after a much shorter distance from the high-lift devices. While the relative angle between high-lift devices and main wing shortened the distance sufficiently to show effect, the distance was too long when they were placed in the current configuration, resulting in no positive impact on lift.
Tentatively, we conclude that canards are more effective than strakes as high-lift devices. However, various limitations undercut the conclusivity of our results. The most major limitation was the slow airspeed of our wind tunnel, unable to induce significant flow separation, causing the effects of canards and strakes to be unobserved. Thus, our research apparatus was incapable of effectively reaching our research goal. Another limitation was the lack of time. Not only were we transferred from an SMP group, COVID has rescheduled our production of experimental apparatus and testing to after August. With insufficient time to fully test our hypotheses, there may be other undiscovered explanations for our results. Other minor limitations exist as well. The strakes and canards were slightly slanted due to the straws that secured them being easily disturbed. The interference from straws during the experiments could have altered airflow patterns through the wind tunnel. The AOA could not be accurately measured and kept. The pressure distribution on the model was uncertain, and there was excessive distance between the high-lift device and the wing. As a result, we suggest the following improvements. After the EYEs, we could continue our research with faster fans, achieving airspeed of at least 10 meters per second. The attachment apparatus of the high-lift device would also be 3D printed to reduce airflow influence and prevent slanting. Finally, the surface oil method would be used to visualize flows as seen from the image on the left. Such a method would allow us to conclusively confirm or negate the presence of flow separation within our experiments.
Our research would not be possible without the contributions of many individuals who have guided us in our research project. The support from our teacher mentor Ms. Huang Yuting during periods of failure and doubt, the assistance of lab staff, and their kind tolerance of our late requests, the advice of our friend Mr. Alex Sai Zhongong. Last but not least, the support of our families in our undertakings. Thank you.